Okay, let us move towards other examples. And another important example is the following. F of x is equal to 1 divided by 1 minus x. Why is it so important? So this function is nothing special, but then you have that f of 0 is equal to 1, and then f prime of x is minus 1 divided 1 minus x to the square, but minus x brings another x here. So f prime of 0 is equal to 1. F second of x is minus 2 divided 1 minus x to the third power, and so again plus. So f second of 0 is equal to 2. F third of x is equal to 6. 1 minus x to the fourth power. Here you know, because the two minus cancel each other, so f3 of 0 is equal to 6. So when you go forward and forward, you have that f j of x is equal to j factorial divided 1 minus x to the 4, so x to the j's power. So f jth derivative in 0 is equal to j factorial. So you have that Pm of x is equal j from 0 to m of j factorial divided by j factorial x to the m. And so this is equal to the sum of x to the m, and here you have that f of x is equal to Pm of x plus Lie law of x to the m as x goes to 0. And okay, here we separated the parts in this way here, but notice that we already knew we already know this fact from high school. Why? We know this simply because we know that 1 plus x squared plus xm times one minus x is equal to 1 minus x m plus 1. So we know that 1 over 1 minus x is equal to 1 plus x squared up to plus xm divided by 1 minus x to the power m plus 1. And we can rewrite it in the following way. This is 1 plus x squared plus x to the mth power and here you have 1 plus 1 divided 1 minus x m plus 1 minus 1. So we added and subtracted this 1. So the first one just reconstructs the sum outside. So here we have sum for j from 0 to m to the power x to the j. And then there are the two others here. And this give just x to the power m plus 1 divided by 1 minus x to the power n plus 1. And this guy here is the remainder. Here we know this remainder explicitly. This is Le's law of x m as x goes to 0. Okay? This is just algebra, just a matter of elementary algebra. But we know this here in the framework of Taylor. And then another example, the second last example I ask you to keep in mind and to learn by heart is f of x is the logarithm of 1 plus x. And again, x bar is equal to 0. Here we are always doing Maclaurin. Okay, everything here is Maclaurin. So f of 0 is equal to 0. And f prime of x is 1 over 1 plus x. So f prime of 0 is equal to 1. F second of x is minus 1, 1 plus x to the second power. So f second of 0 is equal to minus 1. F third of x is 1 times 2, 1 plus x to the third power. So f third of 0 is equal to 2. F fourth of x is minus 6 divided by 1 plus x to the fourth power. So f fourth of 0 is minus 6. So in general, if you go forward, you see like it is like the previous one, except that here there is an alternating sign. And then here we have 0 factorial, 1 factorial with the alternating sign, 2 factorial, and so on. And then from here, you find that Pm of x is sum for j going from 0 up to m of, okay, here you have x to the power j plus 1, because we start from 1. And and then here you have j factorial. You see, because here we have 2 factorial with a third derivative. And here we have minus 3 factorial, so there is a minus 1 to the j with a fourth. So minus 1 to the j divided by j plus 1 factorial, which is in the Taylor coefficient. So write it a bit better. You have sum of j from 0 to m of minus 1 to the power j, and here j plus 1 divided by j plus 1. Or sometimes it is written in another way, completely equivalent, that says j from 1 to m plus 1 in this case. This is of course Pm plus 1, because the final degree is Pm plus 1. And here you have minus 1 to the power j plus 1, this time xj divided by j. And so f of x is equal to p n plus 1 of x plus little o of x to the power n plus 1 as x goes to 0. And a remark, an important remark here, is that often it is important to remember the first terms only of the Maclaurin expansion. So that log 1 plus x is equal to x, and then you have minus x2 divided by 2 plus x3 divided by 3 plus, and so on and so on. Okay, is that the whole formula? And sometimes you can derive it directly again and again. And then the last important formula is the following. You have f of x is equal to 1 plus x to some power alpha. So you have that f of 0 is equal to 1, f prime of x is equal to alpha 1 plus x, and here f of 0 is equal to f prime of 0 is equal to alpha, f second of x is, alpha minus 1 is equal to alpha minus 1, 1 plus x to the power alpha minus 2, f second of 0 is equal to alpha times alpha minus 1, and so on and so on. Okay, and you require alpha, not integer. So at the end, you find that f of x is 1 plus alpha x, and this you have to remember. You already know, but from limits, and now you also have something more. And then you have a plus alpha minus 1 divided by 2x squared, and then plus alpha minus 1, alpha minus 2 divided by 6x cubed, and so on and so on. You have to remember in this way, quite sloppy way. And so, and this is all for what concerns the introduction to Taylor's formula. Now we want to know how to use this Taylor's formula, and the first is the following. It is extremely important: the computation of limits through Taylor's formula. This is very natural, and it is quite surprising because you studied a lot of smart tricks and substitution, change of variable in order to compute very difficult limits, and now you discover that with Taylor's you can get rid of most of them, and computing limit without thinking, basically. So it is just an example. So a limit that at the beginning can be seen as very It's very difficult, but for instance, the limit for x going to 0 of tangent of x minus sine of x divided by x cosine of x minus hyperbolic cosine of x as x goes to 0. Okay, and so we have, so we use sine of x is equal to x minus x cube over 6 plus little o of x cube as x goes to 0. And tangent of x is equal to x plus x cube over 3 plus little o of x cube as x goes to 0. Then tangent of x minus sine of x is equal to x cube divided by 2 plus little o of x cube as x goes to 0. And cosine of x minus hyperbolic cosine of x, cosine of x minus hyperbolic cosine of x is equal to 1 minus x squared over 2 plus little o of x squared minus 1 plus x squared over 2 plus little o x squared is equal to minus x squared plus little o x squared as x goes to 0. So here we have tangent x minus sine of x divided by x cosine of x minus hyperbolic cosine of x is equal to x cube over 2 plus little o x cube minus x squared plus little o x squared times x. This is x cube over 2 plus lidl of x cubed divided by minus x cubed plus lidl x cubed. This tends to minus 1/2 as x going to 0. So this limit is very difficult to be computed with other method, but with this method it is quite easy, and then we will this is a first application, and another application is computation of transcendent quantities. And another application is can be given by this formula, by this problem. The problem is compute E with an error that is less than 1 over 1000. And so here you have E equal to e to the x to the power x equal to 1. This is 1 plus x plus x squared divided by 2 plus x cubed divided by 6 plus x to the m divided by m factorial plus lidl x to the m for x equal to 1. This is Taylor formula how we know it. This is 1 plus 1 plus 1/2 plus 1/6 plus 1 over m factorial plus lidl x to the m. Oh, this is for x equal to 0. For x which tends to 0. Now, the point is that here, with this rest of Peano, well, the remainder term in the form of Peano, here we do not have any possibility of we do not have any possibility of computing the rest of because here we just know that this is a function that goes to 0 quite rapidly when x goes to 0, but we don't have any other information. So we don't know how to say that this rest is less than 1 over 1000. And so we need another version of the rest, and this is the following theorem. Taylor's formula with the rest of Lagrange. So, and it is another way of writing the same rest, and it is extremely useful for this sort of computation, because we say that there is f in Cn plus 1 AB, and x bar is in AB. Then there exists a C in xx bar union x bar x, such that f of x minus Pm of x is equal to f n plus 1 of C divided n plus 1 factorial x minus x bar to the power n plus 1. Okay. So with this formula we can compute E in we can solve this problem here, and so this is the solution of the problem. This new formula for the rest says that there exists a C in 0, 1, because here we have x bar is equal to 0 and x equal to 1, such that E is equal to 1 plus 1, the first two terms, plus 1 half, plus 1 sixth, plus 1 over 24, plus many dots, plus 1 over m factorial, which is the last term of the expansion that we take, and plus 1 over m plus 1 factorial f to the power n plus 1 of C. And this is the error in the form given by Lagrange. So the error is e to the power c divided by, is e to the power c divided by m plus 1 factorial, which is always less than e, because c is less than 1, divided by m plus 1 factorial. So, in order to have an error less than 1 over 1000, m must be large enough. So you must have e to the power m plus 1 factorial less or equal 1 over 1000, which means that m plus 1 factorial must be larger or equal 1000 e. So, of course, the first factorial such that m plus 1 is larger than 1000 e. If you take m equal to 6, then m plus 1 factorial is equal to 7. 7 is larger than, I would say, 5000, because it is, this is 720 times 7. So it is, if I'm correct, 5030, which is larger or equal than 1000 e. This is less than 4000. Okay, so with m equal to 6, we are safe, and so we can compute e as equal to 1 plus 1 plus 1 half plus 1 sixth plus 1 over 24 plus 1 over 120 plus 1 over 720, and this is equal to 2.5, these are the first, plus, here you have 720, 120, plus 30, plus 6, plus 1. So this is 2.5 plus 157 divided by 720, and if you compute it, it is 2.718, and so on and so on. And the mistake with an error, which is surely less than 1 over 1000, but that is much less. And so, as an exercise, I can give you this. Compute sine of 1 up to an error of just 1 over 100. And then we have to prove this formula, and this is the last thing of this part of the lecture, and proof of Taylor's formula with the rest in the form given by Lagrange. So this is the formula. We have f of x minus Pm of x divided by x minus x bar to the power m plus 1 This is equal to, by Cauchy, that says that there exists a C1 in x bar union x bar x. This is f prime of C1 minus Pm of C1, and here m plus 1 divided by C1 minus x bar to the power n. And again, you use again Cauchy, and C2 this time is between C1 and x bar. So this is f second C2 minus Pm of C2, and here you have m plus 1 m C2 minus x bar to the power m minus 1. And then after further m minus 1 iterations, of Cauchy, you get that the polynomial has been differentiated n plus 1 times, so it is 0, the only term that resists a numerator is f n plus 1 of c, and here n plus 1 factorial. So finally, we put all together, and from here we multiply by x minus x bar to the power n plus 1. Finally, we have that f of x minus Pm of x is equal to f to the power n plus 1 of c divided by n plus 1 factorial times x minus x bar to the power n plus 1. And this is the end. Okay, thank you very much.